Dear students, now today we are going to discuss about few examples as discussed in the previous PPT on the basis of those theorems. So example is we find the center of spherical curvature of the curve given by r is equal to a cosine u, a sine u and a cosine 2u. Then how we will solve this problem? Let us look the steps. The osculating sphere, of course, that is r minus c whole square is equal to r square, with center c and radius capital R has 4-point contact with the space curve. As we know, the condition for the sphere of the have the 4 points contact with the space curve may be written as r minus c dot r dash is equal to 0, r minus c dot r double dash plus r dot square is equal to 0, r minus c dot r triple dash plus 3 r dot r double dash is equal to 0. And let us take the center c is equal to alpha I plus beta j plus gamma k. So this is equation number 5. So with these equations now, if you simplify by using 1 and 5 in 2, 3 and 4, just to check it, then we get 3 equations in 3 unknowns. Solving these equations, we get the center of spherical curvature. Using the condition 2, we will get this equation. Just to check it by at your own, just you simplify and check it. So this from here you will get this is equal to 0, which gives you this condition, this relation. This is beautiful relation: a sine u minus b cosine u plus 2 gamma sine 2u is equal to 2a cosine 2u and sine 2u. This is equation number 6. Using the condition 3 in this equation, you will get this relation. Now further simplifying the above equation using dot product, you may be in position to write this equation: a cosine u plus b sine u plus 4 gamma cosine 2u is equal to 4a cosine square 2u minus sine square 2u. Using condition 4, further here you will get this expression as 0. Now simplifying the above equation, we get by comparing a sine u minus b cosine u plus 8 gamma sine 2u is equal to 32a sine 2u cosine 2u. Now using the equation 8 minus 6 gives this equation 6 gamma sine 2u is equal to 30a sine 2u and cosine 2u. Just to check, simplify at your own and check this relation. Since u is not 0, you can't be 0, then 0 or pi by 2 or pi, then gamma is equal to, you can't be 0, but pi by 2 or pi. So gamma, after putting this value, gamma may be 5a and cosine 2u. Now putting these values of gamma in equation 7 and 6, you will get this equation, these equations, this set of equation and their respective values. Using these this value of alpha and gamma, we find beta from the equation 6, and you will get the value of beta cosine u is equal to minus 16a sine power 5u. Hence the coordinates of the center of spherical curvature are, after putting the value here, you will get this as a coordinate of the value of r. Just imagine the unknowns, you already find out all the unknown and you put the value of unknown here. So you will get r is equal to minus 16a cosine power 5u minus 16a sine power 5u and 5a cosine 2u. Now further another example in that connection, that is, if the radius of spherical curvature is constant minded, this is a very beautiful example, then prove that the curve either lies on a sphere or has a constant curvature. How you can prove? The few steps I have shown here. The radius of spherical curvature is given by this. Already we know from the theorems this result, and since r is constant, then differentiating above equation, you will develop this equation 2, and equation 2 shows that either this is equal to 0 or this is equal to 0. If this is 0, then rho is constant, that is the curve has constant curvature. This establishes the fact. And alternatively, if this is equal to 0, we shall prove that the curve lies on a sphere. How? So if a curve lies on a sphere, then osculating sphere at every point of the curve is the given sphere itself only. So it is enough if we show that the osculating sphere is the same at every point of the curve. Since the radius of spherical curvature is constant, so the oscillating sphere has same radius at every point of the curve. So on logic basis, you have established this fact. So the complete so to complete the proof, we shall show that. अब क्या हमें proof करना है? The center of the oscillating sphere is a fixed point given by a constant position vector, and the position vector of the center of the spherical curvature is c is equal to r plus rho n plus rho dash sigma b.